Hello, I'm Roman. Welcome back to the series of building the convolutional neural networks from scratch. And this is the series that is based on the previous one, which was the neural networks from scratch in the Golang. I will continue building different types of the neural networks, specifically, well, this one will be about the convolutions. And in the previous video, we watched what is in general a convolutional neural network. But before we can go and start building things with the code, we need to dive deeper and actually understand all the math behind the convolutions. And if we took a look at what is the convolution in general in the previous video, we still need to understand. Well, actually, we didn't take a look at the operation, but no, we did. But one of the key parts of the model training is the backpropagation, and we need to understand how we should do the backpropagation so we can actually train the model. At least this is the important part for the training process. You don't need this for the inference, but you need this for the training. Okay, so I will use this article called Convolutions and Backpropagation by Pavitra Solai. Sorry if I pronounce the name incorrectly. I'm not good at reading names, but I will try. Yeah, so that is going to be the purpose of this video. This one will be a short one because I'm babysitting and I'm recording this video while the baby sleeps. So I don't have much time actually. So let's go. Ever seen? Okay, so this is, I will skip all of the introduction parts because we already knew why we need to know this. And I think the most important thing about this article is to show you this. We all know the forward pass of the convolutional layer uses convolution, but the backward pass during the backpropagation also uses convolutions, which is interesting. So let's dig in and start with understanding and intuition behind the backpropagation. As for this, we're going to rely on Andrei Karpat's amazing lecture. Okay, so this is the lecture about the backpropagations in general. We're definitely not going to watch it here, and I think most of the things will be the same comparing to the neural networks from scratch book that we studied in the previous series. But if you're already aware of the chain rule in the backpropagation, then you can skip to the next section. So I will skip what is the chain rule in the backpropagation because we already spent, I think, several videos diving into this in the previous one. So we're taking a look at the chain rule in the convolutional layer. Now that we have worked through a simple computational graph, we can imagine a CNN as the massive computational graph. Let us say we have a gate f in that computation graph with input x and y, which outputs something else. A simple function which takes x and y. Okay, we can easily compute the local gradients, differentiating z with respect to x and y as dz by dx and dz by dy. For the forward pass, we move across the CNN, moving through its layers, and then obtain the loss using the loss function. So more or less the same. And when we start to work the loss backwards, layer across layer, we get the gradient of the loss from previous layer as dl by dz. We get the gradient of the loss from the, but that is the same as the backpropagation, like with the dense layer. So when we do the backpropagation, we take the this is why it's called backpropagation. So we kind of do the forward pass, calculate all of the things, and we take the loss and using it as a starting point and going back. In order for the loss to be propagated to the other gates, we need to find dl by dx and dl by dy. Big L. That's actually what they define as the big L here. Oh, so this is the loss. Okay, dz by dx and dz by dy are the local gradients. dl by dz is the loss from the previous layer, which has to be propagated to the other layers. Okay, so we kind of going from the right to the left. The chain rule comes to our help. Using the chain rule, we can calculate dl by dx and dl by the dy, which would fit the other gates in the extended computer graph. So we have like dl by dz, and then we have the derivative from the z by x, same for dy, and this is how we calculate the dl by dx, which is the multiplication of the loss, like if a derivative from the loss from the z multiplied by the d by dx, it's same here. So this is the local gradient and this is the loss. So what has this got to do with backpropagation in a convolutional layer of a CNN? Now let's assume the function f is the convolution between input x and filter f. Input x is a 3x3 matrix and filter f is a 2x2 matrix shown below. So we have the input in general and the filter that we're going to use for the convolution. Convolution between x and f gives us the output O. This can be represented as this, and we have what is the formula? Size of the matrix minus size of the kernel plus 1. So this is how we get 2x2 matrix, and this is the operation, right? So this is input x multiplied by the filter f. Okay, O1, O2. So we have the 4 values. This gives us the forward pass. Let's get back to the backward pass. As I mentioned earlier, we get the loss gradient with respect to the output O from the next layer, a loss gradient with respect to the output, so with respect to this one, get from the previous layer. And combining with our previous knowledge using chain rule and propagation, we get, so this is what we have. Loss gradient with respect to the output, we get from the previous layer, then we have the convolution, and this is where we replaced. So there are still local gradients, and this is, yeah, I think they forgot to change it. This should be dl by do here. As seen above, we can find the local gradient do by dx and do by df with respect to the output O. Do by dx, yeah, this one and this one. And with the loss gradient from the previous layer and using the chain rule, we can calculate those two. But why do we need to find those two values, you might ask? This is used to update. Okay, this finding this one. Okay, very fast. It's actually hard to read. Find the local gradients. Find the loss using the chain rule. Step 1, find the local gradients. This means we have to differentiate output matrix O with the filter F, so backward. From our convolution operation, we know the values. So let us start differentiating the first element O minus O11 with respect to the elements. Okay, so we have the O value O11, and we differentiating it again with respect to all of the elements. Finding derivative with respect to f11, f12, f21, and f22. What is the f here? Filter. Okay, so this is the filter. Similarly, we can find the local gradients for O1, 2, and for the others, so they will be. Using the chain rule as described in our previous examples, we need to find dl by df, as dl by df gradient to the update filter f is the loss gradient from the previous layer, the one that we get from the previous layer, and the local gradient. O and f are the matrices, and do by df will be a partial derivative of the matrix O with respect to the matrix f. On top of it, we have to use the chain rule. This does look complicated, but thankfully we can use the formula below to expand it. So we have the df, like the local gradient, the loss for the filter against a specific element is the sum. Where's the m key? Yeah, let's take a look at the. Why it's I only here? Okay, a little bit confusing. Okay. Substituting the values of the local gradient from equation A we get, so I mean this all looks very similar to what we did with the backpropagation for the dense layer. I mean the formula's a little bit different, but the approach is the same. If you closely look at this to represent an operation we're quite familiar with, we can represent it as a convolution operation between input x and loss gradient. So this is the one that we get from the previous layer, right? Yes, loss gradient from the previous layer, this one. So it means that is not loss gradient for the filter is nothing but the convolution between the input x and the loss gradient from the next layer. Finding the opposite, let me guess, that will be the opposite instead of, oh no, this one is interesting. Okay, we have the local gradients, p differentiating with respect to x11, x2, so well, the opposite. In the previous one, we differentiate against the filter. Right now, we're differentiating against the x. Using the chain rule for every element of the x, we have something like this. Again, this is the local gradient. Expanding this and substituting from the equation B, we get, well, this is different, but it looks like the convolution again, but different. I mean, you can see the pattern. So there is 1, 2, 1, 2, 4, 2, 1, 2, 1. So there is definitely some pattern. Now we have the values. Believe it or not, even this can be represented as a convolution operation. dl by dx can be represented as full convolution between 100 rotated filter f and the loss gradient. Okay, so the loss gradient is that's what we get from the previous layer or from the next layer, and rotated filter f. First, let's us rotate filter f by 180 degrees. This is done by flipping it first vertically, then horizontally. Okay, so we just, yeah, well, I guess you can represent it as the just changing the indexes. Now let's do a full convolution between the flipped filter f, which can be visualized as below. It's like sliding one matrix over another from. So it kind of goes beyond the filter f with the loss gradients. Yeah, because if it's not the full convolution, then the normal one will just end up having one element, right? The full convolution above generates the values of dl over dx, and hence we can represent it as filter. Okay, full convolution. Well, now that we have, because I mean the sizes of the grade of the gradient and the input, they should match. So here we have 3 by 3, and that was the same for the input. And we have filter 2 by 2, and the same we had, where is it? Otherwise we won't be able to actually use those gradients to adjust the weights, well, adjust the parameters. Both the forward pass and the backpropagation of the convolutional layer are the convolutions. So, I mean, this is kind of still fascinates me. Like, there is a long, well, probably not the long chain of some math equations, but in the end, you end up, like, so the backpropagation is the convolution between the input. So, for example, gradient for the filters is the convolution between input values and the loss gradient that we get from the next layer, and the gradients against the input values is the full convolution between rotated filter values, which was the input for this layer, and again the loss gradient that we get from the next layer. And that's it. Hope this help to explain how backpropagation works in the convolutional layer of a CNN. If you want to read more about this, do look at these links below, and do show some love by clapping And this article, can I clap? How many times I can clap? Okay, I hope that's enough. Okay, so I mean, in general, if we put aside all of the kind of math, because we don't have to implement like all of the things that were described here. So we have the convolution for the forward pass, which is convolution between input x and the filter values. And then we have the backpropagation, which is where we need to calculate two different gradients, one for the inputs, one for the filter. And this is just two convolutions between more or less the same values. I mean, instead of the convolution between the inputs and the filter, we have the convolution between input values and the loss gradient that we get from the previous one, and the rotated convolution and full convolution between the filter and the loss gradient itself. So it's still, I mean, it's still just one operation of the convolution. And that's it, right? So what is this? Okay, this is from Mr. Decoding the engine behind the neural networks, backpropagation. So I think this is, yeah, so this is in general describes what is the backpropagation is. Again, there is a code with the Python, because what else you can see here? So there's, yeah, and there is some probably nice animation, but we're not going to take a look. So I'm going to close this. This one again is called Convolutions and the Backpropagation. If you want, you can take a look by yourself. Don't forget to clap or leave a comment if you're a member of the Medium, which I'm not. And I found actually another good article. I mean, I scanned it quickly. It's called What is the Convolutional Neural Network? And that's more or less describes what we took a look in the previous video. So it takes a look at the convolution itself, at the ReLU activation function, the softmax, what is the pooling layer, no I'm not, flatten layer, and that's it. So I think this is the good one. Just to have a recap. And if we go next, I think there is this one, a complete guide, or actually, oh, this is the one that we took a look. Again, it's called Convolutional Neural Networks, a comprehensive guide. Take a look at this too. But in the next video, actually, I have another article where we can see actually the Python code. I mean, let me find it. And this is the one. It's called the Build Convolutional Neural Network from scratch using Python. Well, the only thing that's different for me will be using the Golang. And what is this? And this one actually, I mean, this is the one probably I will use as the guidance to build my implementation, because it works against the same problem. So they will want to use the fashionless dataset to build the classification, and then there is the convolution building, there is a forward path, there is the backward path. This one building the max pool layer, it will took a look at this backward path. Oh, actually, yeah, we will need a backward pass for this one. Building the fully connected dense layer, which we already have. We have the forward pass in the dense layer, but those are implemented. Cross entropy loss, we have it, and there is a train function, predict, perform classification, blah blah blah, training. So this what we have. So in general, there are things that I need to implement is the convolutional layer itself, like forward pass and backward pass, and this one could be tricky since I'm using the Golang, and I will need to think about the how I would represent the data. then I actually need to build the convolution, because if you take a look at this, there is a correlate to D function, and if I remember correctly, this one actually does the correlation and the convolution. There is correlate to D. Yeah. So this is the function that implements the convolution. But when I did a quick scan through the Golang, I actually didn't find any existing implementation of the convolution for the Golang. So I will have to implement it by myself, which is interesting. With the max pool, there is a bunch of the loops, shouldn't be a big problem. There's backwards, same. And yeah, so once we have the convolutional layer, then we have the max pooling and flatten. We will need flatten layer to connect it, connect the convolutions with the dense layer. This one is the most simplest because we actually don't need the backward pass, and then that will be a layer just to transform the data between the different types of the layers. And in general, that's it. That should be enough for me to change the model architecture that I have before to do the classification for the fashion mean dataset and change it to the convolutional neural network architecture. Let's see. Okay, again, this is the short video. Don't forget to check the main channel. If you enjoy the content that I'm doing, you always can support me with the Ko-fi page. You'll find all the links in the description, as well as the link to join the Discord server, where you can DM me, ask any questions, talk with me or with the other guys that we have on the server already, and I will be glad to see you there. But for now, thank you for watching, and I see you in the next video. Bye bye.